Thank you. It's a great pleasure to be back here. I started here more than 30 years ago as a student. It's also a great honor to be here because this university has a lot of successful graduates, August graduates, and so it's an honor to be chosen to give this lecture today. I'll talk about fluid dynamics, which is one of the areas I've been working in recently. And I'll start with very elementary stuff because I understand that there are people from many different areas of science in the audience today. So I'll just start with something very simple. We have some kind of profile that, let's say, do I have chalk? Yeah, I do have chalk. So let's say we have a tsunami wave just going on the open ocean. It doesn't do much, it just travels. It travels at a constant speed until it, until it hits the coast. And so it has some kind of profile. Can we do something about this? So it has some kind of profile, call it capital F, which is a function of space. It would be a function of two spatial variables, but let's just look at it from the side, so it becomes a function of one variable. And this profile is just traveling at a constant speed. So it looks like capital F of x minus vt, where x is the spatial variable, and t is time, and v is that constant velocity. And so if I want to write it as a function of space and time, then that's the function little t up there. And it has a very simple form. And it satisfies a partial differential equation, which is in the middle of the slide. So there is a partial derivative with respect to time and partial derivative with respect to space, the spatial variable. And if you know how to compute partial derivatives, then you can easily see that the first one is the derivative of the function capital F of that profile at the point x minus vt. And then you have to differentiate inside the argument. And you differentiate with respect to time, so you pick up a minus v in front of it. Okay? The second partial derivative is just f prime at x minus t because you differentiate with respect to x inside the argument, it's just 1. Okay? So if you multiply the second one by v and add them, you get 0. Okay? So that's a very simple equation that this function satisfies, and it's called a transport equation. Because it transports some kind of profile. Okay? You can do this in one dimension, in space, and then you have a second dimension, which is time. You can do it in more dimensions in space. So here, for example, I'll be talking about 2 dimensions, so that's what we'll do here. So let's take now the velocity being a vector, that's up here, this bold v, and then we need to do an inner product or dot product or scalar product with the gradient of the function f. The gradient is the spatial gradient, so this is now a function of 3 variables, time and 2 spatial variables, and so gradient is with partial derivatives with respect to the spatial variables, x1 and x2. And I want to simplify things a little bit, so you see partial derivatives are written like that, so I will instead write just f sub t and f sub x instead of partial f, partial t, partial f, partial x, and I will ditch the arguments as well. Okay, so the equation up there is written there in the red. It looks a little bit neater that way. Okay, and so I can write it then if I have more spatial dimensions, I can write it like this. There is the velocity vector, which is a constant vector, just some vector in 2 dimensions. And then I have the gradient, which is the partial derivatives. And if I dot them, then I get a function profile that travels in a direction of the vector v with the speed, which is the length of the vector v, in 2 spatial dimensions as time progresses. And this is of course all very simple, but I can make it a little bit more complicated if I decided my transporting vector is going to be dependent on space and time. So it's going to be a function of x and t, and then things won't be so nice anymore because then my profile, capital F, will not be just transported at a constant speed, but it will be also changing. Okay? I can now solve this equation, and for example, if I'm mixing something, right? I have some liquid, and let's say I have some ink in that liquid, and I want to mix it, and I'm asking what is the density of the ink in different positions in that cup. And if I mix it, then of course the density will be some complicated function of space and time. Now that is subject to not just the mixing, but also diffusion, because the ink diffuses. We won't have diffusion here today because sometimes diffusion does not happen. And at other times, diffusion may take a long time for us to see it. So if we want to model something on some physical phenomenon on a short time scale when we don't see diffusion, then we can just ignore it for that short time. Okay, so that's what I'll be talking about here today. There will be no diffusion. And one more thing before I pass to something a little bit more complicated. All this kind of equation, I can state it for either a scalar function f, that means just with real values. I think in Slovakia I have to mention the scalar is not an aquarium fish. It's a real valued function. I can also do it for a vector valued function. So my f could be a function that has values in a vector space like 2-dimensional, 3-dimensional Euclidean space. Okay, so now let's go to something a little bit more complicated. So now we have the same setup, but this function f will be the same as the velocity function which is advecting it, okay, or which is transporting it, right? So here in the previous slide I was saying that, well, that velocity might be just a vector or might be a function of space and time. So let's go to that setting where now it's a function of space and time, and let's say that the function f that is being transported is actually the same function v. So that means the unknown function f is transported by itself, and then I'm calling it v, that's the velocity, right? So when is this appropriate? Well, in fluid dynamics. Because if you have let's say a fluid molecule that moves at a certain velocity v in this location in space, and then you wait for a bit, then if the velocity, let's say, is in this direction, then the molecule will move. And then the molecule at this point in space, which is different than here, has that velocity v, right? If it's not changing its velocity. So that means the velocity is moving through space and being transported by itself. The faster the particle moves, the faster the velocity gets transported from here to there, okay? So suddenly I have the equation up there, and that's called Berger's equation. Okay? And again, think about v being a 2-dimensional vector-valued function. Okay? And so when we want to solve the Berger's equation, we are solving this equation. We are maybe giving some initial condition, initial value. So let's say the velocity everywhere in space, if I'm in 2 dimensions, so it's a 2-dimensional space. Maybe I have some liquid that is moving around a thin plate. Okay? And of course, in 3 dimensions, you can do it as well, but it becomes more complicated. So at this lecture, I will only talk about 2 dimensions. And so initially, every point in space has some velocity. That's the velocity of the molecules that are at that point, in which direction and at which speed they are moving. Okay, and then I'm asking what happens later, right? The velocity is going to be evolving with time. And solving that partial differential equation means finding how the velocity looks like at any later time. Okay, so as I said, that's called the Berger's equation, but that may be not a name you have heard. You have heard maybe before Euler's equation or Navier-Stokes equations. And the reason is that Berger's is not so well known because it doesn't quite model fluids very well. The reason for this is that liquids are incompressible. And even air which is a gas, is very close to incompressible in fact. So if you have air moving at very fast velocities, like for example, you have an airplane, a jet flying through the air, then at those velocities, air is sufficiently compressible that you can see that compressibility in the model that you have to use. Okay? But if you are just sort of moving your hand and asking how the air is moving around, or even at faster speeds, if a car moves through the air is very close to actually incompressible. So if you have heard, for example, about hurricanes, how the pressure in the eye of a hurricane drops even for the strongest hurricane, the pressure doesn't drop much more than 2% from typical atmospheric pressure. So liquids are definitely essentially incompressible, and even gases can be incompressible. So because of this incompressibility, if you are trying to move some particles, some molecules of air or water, they will push on other molecules. And so there's going to be this interaction which creates pressure. And so pressure is this P term in the red equation near the bottom. And you need to incorporate that into your model. So that means you need to figure out what the pressure is if these molecules of water are moving around at given speeds, velocities, okay? And that looks a little bit weird. You see that equation there because there is a VT, so that's a partial derivative of the velocity with respect to time. That sounds like we could compute the velocity as time progresses because it tells us how the velocity changes as a function of time. Okay, and it tells us, well, let's say the Burger's equation is equal to minus the other term, v dot gradient v, right? Whatever that term is, in fact, the gradient v now becomes a 2x2 matrix, and then the v is a vector, so that dot product becomes a vector, two-dimensional vector. Okay, so the time derivative of velocity there is just minus v dot gradient v, okay? And here it has an extra term, pressure. You might ask, why is there a minus gradient P? Well, think about it this way. What is a gradient? Right? Pressure is some scalar function. What is a gradient? It points in the direction in which a given function grows the most. Okay? So gradient points in the direction of larger pressure. But where there is larger pressure, I get force pointing in the opposite direction. So minus gradient P is the direction in which my fluid forces itself. Okay, so that means I need to add that to the acceleration of the fluid. Acceleration is time derivative of the velocity. So Vt, time derivative of velocity, has an extra term which is minus gradient pressure. That's why the equation looks like that. Okay, and so all this is well and good, but I don't have any P sub T term. I don't know how the pressure evolves. Okay, but it turns out it's okay because I have an extra equation to add to it, and I can use that equation to find the pressure. And the extra equation is the incompressibility equation, because I told you I'm putting in the pressure because my fluid is incompressible. So I need to encode that mathematically somehow. I get an extra equation, and this equation is down here. That's called divergence of the velocity being 0. What is divergence? Well, it's applying this little triangle, which I called gradient before, so it's really, and I apologize for this, so gradient of some function. What did I do? I took the partial derivative with respect to first and second spatial variable, right? And I applied it to the function. I'm applying the gradient vector to the function, and that means if I take gradient f, I think I had it on the previous slide, right? Gradient f is partial derivative with respect to first and second spatial variable. But now I'm doing a dot product or scalar product, so I'm doing it with the velocity, which is a two-dimensional vector. So I take this partial derivative applied to the first coordinate, which is here, and then the second one applied to the second and add them up. Okay, so this is called divergence. Now, what divergence tells me is how much of the fluid is being created or destroyed. If it's 0, then none is being created or destroyed. Or in other words, if I have, let's say, a two-dimensional region, and I'm asking how much fluid enters and exits that region at a given time, I just need to integrate the divergence across this region. And if the divergence is 0 everywhere, then the integral of the divergence will also be 0. So that means as much fluid is coming in and out of any region in the plane. Okay? And that's precisely what I should have when the fluid is incompressible. Okay? I cannot ram more fluid inside the region than I had there before. So this is the second equation I need. It's really the third equation because the first one here involves two equations. It's a two-dimensional vectors. And this is good enough, and these two equations together are called the Euler equations. They model incompressible, inviscid fluid. Inviscid means there is no viscosity. Okay? So water is very close to being inviscid, so it works well for water. Honey, not so much. Okay? Honey is very viscous. Okay, so these are the Euler equations, but as I told you again, the pressure looks really annoying there because I don't have any partial derivative with respect to time of pressure term. There is fortunately a way to remove it. And here's what you do. You apply this operator called grad perp. So what is perp? Perpendicular. Okay, so what I do, I just take this, I think of this as a vector now. It's a vector of differential operators, that's fine. And I do the same I would do if I wanted to take a vector in a plane and rotate it by 90 degrees. Right? How do I rotate a vector by 90 degrees? Let's say it's a vector AB. Counterclockwise 90 degrees. Right? What is this vector going to be? Well, I take my A, put it here. I take my B, put it here, and put a minus. Okay? So that's the same thing. I take my gradient vector, which was this. I put this one here, put a minus, and put this one here. Okay? That's called the grad perp operator. And the reason I'm applying it is because it will get rid of the pressure. You see, if you take grad perp of the pressure in blue up there, not of the pressure, but of the gradient of pressure, then it's pressure, partial x1, and then partial x2 with a minus, and then plus pressure, partial x2, and then partial x1. So the two mixed derivatives are equal, so they will cancel, and pressure disappears. Okay? And I can therefore take my equation here, this red equation, Vt plus etc., apply that operator, the grad perp to it, and the right-hand side will become 0. Okay? What happens to the left-hand side? Well, if I do a few computations, I find out that, well, the Vt terms just become time derivative of the grad perp of the velocity, and that has a name as well. That's called the vorticity. And vorticity of a fluid in 2 dimensions just tells me how much the fluid is rotating. The larger vorticity, the more it's rotating. The larger negative, the more it's rotating the other way around, locally at every point. Okay? And then I fix time and I ask, how is the fluid rotating in different points in space? That function is the vorticity function. Okay? So this all has physical meaning. And so that term that was here, the Vt, becomes just the time derivative of the vorticity if I apply the grad perp operator to the equation. And then the second term, if you do the computation right, becomes velocity dot gradient of the vorticity. So suddenly, this is the same equation we had at the beginning, right? The transport equation down here. It's a simple transport equation, but my transporting velocity, of course, is not a constant vector, it's some function. Okay? But at least the pressure is gone, so that's very nice. And of course, there is a conservation of difficulty. And so what's complicated here is the relationship of the velocity with the pressure. You see, before I told you, let's just take this constant velocity, or let's take some velocity which maybe somebody gives us, right? You mix some cup of water, and maybe you can exactly write down what the velocity is you're imposing on that water. Okay, but now this velocity is related to the vorticity. The vorticity is now the function I'm trying to compute, but the velocity that is moving the vorticity around, that's intimately related to it. There is a relationship between those two. And I need to write down that relationship. And in fact, at least formally, it's not too difficult to write it down. Because remember, the velocity and vorticity are related in such a way that's up there. The vorticity is grad perp of the velocity. Okay? So it turns out that as a result, I can find also the velocity from the vorticity which is going in the opposite direction. I take inverse Laplacian. Now, what's inverse Laplacian? Well, maybe you know all what Laplacian is, right? It's just second derivative with respect to one spatial variable, second derivative with respect to second spatial variable, add them up, okay? I can always do that if the function has two derivatives, okay? So that's Laplacian. And inverse Laplacian is the inverse of that operation. I will not go into details here, but it can be done. And if you take inverse Laplacian and then add to it the grad perp, then that gives you velocity from the vorticity. The reason for that is, if you take inverse Laplacian and grad perp and another grad perp, that means out of the velocity you should get the vorticity with the other grad perp. Let's check whether that's true. Well, two grad perps make a Laplacian. So that exactly cancels the inverse Laplacian. You can easily show that grad perp is just up there, and you just apply that operation twice, and you get the Laplacian. Okay, so this works. In fact, there is a formula. If you don't like that formal version of this, there's a formula for that. This won't be too important here. I'm just showing you that there is a formula. You can compute velocity from the vorticity using this formula here. This is in 2 dimensions. It looks a little bit different in 3 dimensions, but it's a similar relationship. You just have to take you fix time, and at that fixed time, you take your vorticity and compute velocity at any point x using this integration. Okay? That's why this is called a non-local equation, because the velocity doesn't depend on the vorticity just at the same point x. The velocity at point x depends on the vorticity everywhere in the plane. Okay? And the kernel that's there in front goes to infinity if my integration variable y goes close to x, because y minus x perp, that's just a vector y minus x turned 90 degrees. But at the bottom, you have y minus x squared. So the top vector in the fraction has length y minus x, and the bottom has y minus x squared. That means the bottom is much smaller if y is very close to x. Okay? So it's not a trivial relationship, but one can work with it, and people have done that for a long time. And in fact, most of the main questions about this equation in 2 dimensions have been answered. In 3 dimensions, there are a lot of open questions. But in 2 dimensions, most of them have been answered. The kind of questions people ask about partial differential equations usually are, do solutions exist for a short time, for a long time, right? Could solutions stop existing at some point? Well, for the Euler equation in 2 dimensions, no. In 3 dimensions, that's of course one of the biggest open questions in all of mathematics. In 2 dimensions, yes, solutions exist forever. And you can ask even how fast can they grow, whatever that means. So in this case, this is a transport equation. The vorticity just gets moved around. The vorticity doesn't grow. But you can ask, can the derivatives of the vorticity grow? Because if 2 points of vorticity were, let's say here it has value 1, here it has value 0, if they come close to each other, then the derivative of vorticity can grow. Okay? So we know that as well. Derivatives of vorticity can grow at most double exponentially time. This was known for a long time that no faster growth than that is possible for almost 100 years. And in the last 10 years, we found out that actually such double exponential in time growth is possible. Double exponential in time is e to t. This is a very fast rate of growth. But it is possible to achieve it. This was proved about 10 years ago on bounded domains, and it was proved about 4 months ago by myself on unbounded domains, but still with domains with the boundary. And in fact, there's one of the still left open problems in 2-dimensional fluid dynamics. If you are on a whole plane without a boundary, which is what I'm talking about today, we still don't know whether solutions can grow double exponentially. If you prove that, then for the students, maybe you can become a professor in Princeton or Harvard or MIT. So it's a big open question. Okay, so let me now continue. How much time do I have? Is that correct? Yeah. Yeah. Okay. So let me now move to another equation, which is related to the Euler equations, but it models a slightly different fluid model and fluid phenomenon. So, but it's still a transport equation with a velocity which depends on the quantity that is being transported. And I think I have it on the previous slide here. That's called an active scalar, right? Scalar because it is real valued quantity. The vorticity here is real valued. And active is because the velocity is being generated by the scalar that is being transported. So as opposed to passive scalar. Okay, so this is another active scalar equation. And it is called the incompressible porous media equation, or IPM. And now rho is the scalar being transported, and it is a density of the fluid. So in the Euler equations, we assume that the density is constant in the case of incompressible Euler equations. If we take compressible Euler equations, then of course density is changing because we can compress whatever gas is being transported. Okay, so here the density is the main quantity you are interested in. I will call it rho. And so it's a fluid or a liquid that has variable density. And it is being transported by a velocity that is being generated by it, but in a different way than in the case of the Euler equation, when my velocity was generated in this form, this red equation here, from the vorticity. Okay, so here it will be a little bit different. And what this equation models is transfer of fluid through a porous medium. So some kind of aquifer, vodonosná vrstva. Usually that's made of limestone, where there is groundwater under our feet. Okay, and the liquid groundwater is being transported through it. And in many situations, the density of that water is not dependent on anything, so it's just constant. Okay, if it's just fresh water in an aquifer, then that's just constant density. So that's not very interesting because then my rho is just a constant function. But in some situations, it is a function of space and time, so the density is variable. For instance, you can have salt water entering an aquifer if it's near a sea, near an ocean. And then the salinity level can vary in the water, and as a result, the density varies as well. The other, even possibly more important application is when you have water and oil in an aquifer, right? So for example, you are trying to extract oil, and you get groundwater coming into the region where you took the oil out. So suddenly you have two liquids. And that's actually a special case of this equation. It's called the Muscat problem, where the two liquids don't mix. So your density is not a continuous variable function, but it just takes two values. There's density of water, there's density of oil. And there is an interface between them. So let me first talk about the continuous case, but then I'll move on to this second case when we have an interface. So in the continuous case, it turns out the right way to relate my density and velocity is up here. The velocity is minus gradient of pressure. You have seen that before. And then there is also minus 0, rho. This is basically just the force of gravity. The denser regions are being pulled down, right? So the second coordinate that's down. First coordinate is horizontal, second is down. Again, I'm only in 2 dimensions. You can do this in 3 dimensions as well. So the denser regions are being pulled down faster or more strongly. So that's why I'm adding that to my right-hand side here. But what I'm getting here is this time not the acceleration of the liquid, but it's the velocity of the liquid. And the reason for this is that the model is happening on a large scale in space and time. And on those large scales, the acceleration really becomes a velocity because I will wait for a long time, so that means I'm gaining certain velocity, and that velocity will be moderated by my porous medium because the water cannot flow very fast through a porous medium. Of course, the limestone is going to slow it down. Okay? So this is the right model on the large space-time scales for this phenomenon. And so therefore, I have this relationship between the density and the velocity, but there is still this annoying pressure, but I can again get rid of it the same way I did before. So I take my velocity and apply this grad perp to it. So I'm computing its vorticity, okay? And that means I take the right-hand side and apply grad perp to it. And I know that the pressure or the gradient of the pressure will go away if I apply grad perp. So that's great. What happens with the gravity term? And I'm assuming the gravitational constant is 1 here. So otherwise I would have to carry around a g. So I don't do that. Okay, so what happens with the gravity term? Well, I just have to apply the partial derivative with respect to x1. Remember what was the grad perp? It's right up there, right? So I have to apply that to the second coordinate of my vector 0, rho, because the first coordinate is 0. Okay, so I get just x1 derivative of rho and with a minus sign, okay? And that's great, because now I know what the vorticity is of the velocity. It's minus rho partial x1. And so I already know from the previous slide, once I know the vorticity here, I can compute the velocity out of that by applying this Laplace inverse and grad perp operator. So there is a way to do it, that's the point, right? So I can express the velocity from this density in such a way. But the problem is this is a more singular model. Okay, why is it more singular? Because you see here, the vorticity is being transported and the velocity is computed from the vorticity by applying Laplace inverse, which is like making the function better by 2 derivatives. If you take Laplacian, you are differentiating twice. So if you take the inverse of Laplacian, you are improving the differentiability by 2 derivatives. And then you take grad perp, which is like taking 1 derivative. So the point is, this whole operation sort of adds 1 derivative. That means your function becomes better. The velocity is better by 1 derivative than the quantity being transported. Okay, so the velocity is nicer, and when the transporting velocity is nicer, then things are going to be nicer. Now, here, for this IPM equation, it's a little bit different, because you are doing the same, but you are first differentiating your density with respect to the variable x1. So the 1 derivative you are gaining, you are losing it by this differentiation. So the velocity has the same level of regularity as your density. And this becomes a problem when we are talking about this Muscat problem. Again, this is an important, as far as applications are concerned, an important form of this equation because it is being used in petroleum extraction. And so there, my density just takes 2 values, right? And so it's discontinuous at the interface of oil and water. Okay? And therefore, my velocity will also be discontinuous. And that creates a problem if I want to transport something with a discontinuous velocity. Okay? But there is also some positive. The positive is that if I'm only talking about the, let's see, the case when I have, let's say, oil here and water here. So oil has density rho 0, water has density rho 1. Rho 0 is less than rho 1. Okay? So I don't really care what the transporting velocity is here or there, because it just transports water here and oil there. It doesn't really change anything, right? The density of water is constant, so it doesn't matter. What matters is what the velocity is here, because I want to know how it transports that interface between water and oil. Okay, so I need to only worry about how this interface is going to be transported. So I'm calling omega t the region up here where I have the water. And so this boundary of the region, that is what I'm interested in, how it gets transported by my velocity. But now the problem is that, as I said, the velocity is discontinuous, and you can also see it by taking that rho sub x1, that derivative of the density with respect to x1. If my density is a nice function, then the derivative is also a nice function, but here I have a jump. So if I differentiate in this direction at this point, I get a delta function, Dirac delta function. because a derivative of a discontinuous function is a delta function, right? It's kind of like when you take, it's down up here, right? So you take the absolute value of x in one dimension, and you differentiate it once, you get -1 here and +1 there, right? And you differentiate it again, you get 0 here, 0 there, but then you get delta function, in fact, 2 times delta function at 0 right here, okay? So it's the same problem, but your delta function is now living on this whole interface. But it's okay because remember you're applying a inverse Laplacian to it, and that gains you 2 derivatives, so it makes the function much nicer. So even though it's a delta function which not really is a function, it's still okay. So this all can be taken care of, and many people have, especially in the last 20 years, there has been a lot of work on the incompressible porous medium equation, and specifically on the Muscat problem. I can't list all the papers here, so I'll just tell you about a few of them just very quickly. The point is there are 2 distinct regimes. There is the stable regime and there is the unstable regime. The stable regime is when oil is above water. Unstable when water is above oil. Water is heavier, okay? So when the heavier fluid is about the lighter one, then mathematically this is a complete Wild West. It's what we call an ill-posed equation. Turns out you cannot find unique solutions. If somebody gives you initial data, what is initial data? It just tells you what the interface is at time 0. And then they ask you, well, compute what the interface is going to be like at later times. How is it going to move? And it turns out there is not a unique solution. So this is an ill-posed equation in the unstable regime. But if you're in the stable regime, then it's well-posed, at least locally, which means locally in time. So at least for a short time, if you start with oil being above water, the lighter fluid above the heavier one, for a short time you can compute how this interface is going to move. And in fact, if the interface is sort of reasonably flat to start with, then you can actually extend that forever. What will happen? The interface will flatten more and become nicer. But if the interface doesn't start close to flat, then you might run into some issues. So, for instance, it can overturn in finite time. So if your interface starts very close to vertical somewhere, it's not just this simple, you have to figure it out. Actually, it has to be more like this. But anyway, it's possible that it will overturn. And once it becomes like that, then right here you have this unstable region where water is above oil. And again, all hell breaks loose. Your solutions will not be unique anymore. And so mathematically, it's chaos in a sense. Something can still be done, but it's not as satisfactory. Anyway, but if you stay in the stable regime, then it's still an open question whether that can happen, not the overturning, but whether some kind of singularities can happen, right? So that's the other possibility how your solution may stop existing. You might develop a singularity of the interface. Maybe after the interface starts looking like this, and then at a later time becomes a corner. Maybe that's possible. Okay, that would be a singularity. Maybe it will develop a cusp that will be even a worse singularity. Okay, so that's still an open question. Again, one of the big open questions here. But never mind. Let me tell you about how one works with this, not knowing whether singularities might happen or not. Okay, so again, let's talk about the stable regime, because once we are in the overturned regime, then again it's chaos. So let's talk about the regime where water is below oil. Do I have an eraser somewhere here? Oh, here. So let's talk about that regime. And then my interface, remember I'm in 2 spatial dimensions, so one of them is horizontal, one of them is vertical. So my interface now becomes just a function of my variable x, my horizontal variable x. So I'm only interested in what the interface looks like, so I can just ask, how does this function change as time progresses? So I'm modeling it as a function of time and one spatial variable now, rather than modeling the density as a function of time and two spatial variables. I'm just now asking, where is the interface located at some time t? Okay, and again, you have to do some work, which I'm not going to tell you any details of. That's not the point of this lecture. But you can write it down. And turns out this is the equation for that interface, right? So you're asking, how does this interface move as a function of time? So if you, is this point moving up or moving down? Each of these points, is it moving up, is it moving down, right? Well, you have to compute the time derivative of that function. This is the function of x at any fixed time. And you want to compute the time derivative of that. So that's a partial derivative. And there is some kind of complicated integral here. So this is actually an integral differential equation. There is a derivative of the function fx in there at the point x, at any other point x minus y. You integrate, there is a fraction. It's a little bit complicated. You have derivative of inside an integral. That's why it's called an integral differential equation. Okay? And again, this is not a trivial equation because remember, as I said, this whole model is more singular than the 2D Euler equations, about which we know a lot, almost everything. And by the way, the reason why this becomes a problem, because remember, I told you for the Euler equations, derivatives can grow very, very quickly in time. And this is more singular. So in fact, here derivatives could grow, theoretically at least, even faster than that, or possibly blow up in finite time. That would be a singularity if some derivative becomes infinity. Okay, so, so it turns out, if you do this computation, that how do you compute how this interface is moving? Well, remember, we have a way to compute this velocity from my density. And it turns out the velocity does have at each point on this interface a discontinuity. Remember, I told you if the density is discontinuous, here density is rho 0, here is rho 1, it has a jump, then the velocity will also have jump. But luckily, the jump only happens in the tangential direction to the interface. The normal direction of the velocity is continuous across the interface. And that's the only direction I care about, because I don't care whether the interface is moving like this. It stays the same, right? If you take a line and move it along itself, you don't change it. It's the same line. What you care about how fast the line is moving in the normal direction. And so in the normal direction, you can actually compute the velocity nicely. And that is precisely what gives you this equation for the interface. Okay? But as I mentioned to you before, this equation is more singular. In fact, it's what we call supercritical, because I told you that the velocity has the same order of differentiability as the density. Density has a jump, velocity has a jump, and if you know something about differential equations, you know that if the velocity is Lipschitz, then we can solve the equations nicely. Lipschitz just means that the velocity at two distinct points in space differs by no more than some constant, call it L, times the distance of the 2 points. Okay? This is far from that. The velocity is, am I supposed to finish? Really? Okay. Then I didn't get to my main point, but maybe that's okay. So I'll just finish very quickly. So the point is, turns out you can show that singularities exist, but you have to work on a half plane. Half plane is relevant when we have aquifers with rocky bottoms, which aquifers always are. And then this interface might look like this. And you might have oil here, and you might have water down there. As you are extracting the oil, the water is coming from the sides, from some further away area. And it turns out if you have this kind of motion, then after some time, these two fronts will meet, and they will create a singularity right here. So it turns out that you can have a singularity in this equation, and I proved it a couple of years ago, well, a year ago, and I won't get to the details, but it's still an open question if you don't have this bottom, which of course, again, is not quite what you have in reality, but mathematically it's a very important question, then the singularities are still open. And that's it. Thank you.